So let's talk about the Linux kernel and when it becomes relevant, right? And in an attempt to do that, what we'll do is we'll imagine that we have a very simple system. So the system has a CPU, it has a DRAM, right? So this is all of this is DRAM, and then it, let's say, has a ROM, right? And then let's say it has the SSD. Right. So let's briefly talk about what the Linux kernel is. Right. What is the kernel? What should you imagine when we talk about kernel? So we'll keep the model very simple. We'll keep, you know, we'll ignore a lot of details and focus on like the fundamental things. So a kernel essentially provides us with a scheduler, and a scheduler manages processes. And the other thing that the kernel does for us is it allows us to manage hardware, right? So it allows us to manage hardware. And let's take a look at this part now. So let's say you have a machine, right? Let's say you have your workstation, laptop, something like that. And to that, let's say you have connected a camera, right? And so what we now want to do is connect this camera over the USB and then fetch frames from within that camera, right? And this camera can be of any company, right? It can be from X, Y, Z, so on and so forth. And it would be fair to imagine that if you have the kernel running here, the kernel needs to know about what kind of camera this is. And once it knows about what kind of camera it is, it also needs to have some code that helps it manage this camera. My claim at this point is that that code which helps it manage this camera is called the driver. Right. We'll speak about this a lot more later in other videos, but this is the notion of driver. So we are going to manage hardware using kernel drivers, right? And so somebody needs to load it in and so on and so forth. That, we are going to take a look as part of this series. But this camera, hopefully you're convinced that there is a USB port here, and then we need some code that can manage the USB port, and that's another kernel infrastructure, or again driver, right? So something like that. All right, so this kernel then is essentially, we can think of it as it manages processes and it helps manage the hardware, right? Okay, so question then is, where is the kernel stored? So the answer to that is that the kernel is stored, let's say, as an image in the SSD. So, it's not really an image. It can be a bunch of files and so on and so forth. So essentially, bunch of files, and that's the kernel saved in the SSD. That is important. Then the question is, but the executable code must come to DRAM. So the kernel needs to be loaded to the DRAM, and from the DRAM, the CPU will execute stuff. Okay. And then there is ROM, and ROM is also connected, or like the CPU can reach out to ROM, and obviously CPU can reach out to the SSD. The question now we are wanting to explore is, at what point does the Linux kernel come from here to here? So let's talk about what happens after power on. So we turn the power on, and bunch of things happen, and let's say the CPU is powered on. So the CPU, essentially, what it'll do is it'll go to the ROM, fetch the code from there, and start to execute. And what kind of code is available here? The code that is specific to that system, which the system maker has provided. The system maker can be Intel, it can be Lenovo, it can be AMD, so on and so forth. Whoever creates that motherboard kind of a thing is the one that will they that who are supposed to know how the CPU is supposed to kind of boot up and proceed. So one of the things that the ROM code has is turning other things on. right? And remember, the DRAM needs to be turned on for the Linux kernel to be copied here, right? And again, go back and remember what the Linux kernel does. It's just for management of processes, and it handles devices, or it helps us manage hardware. But this functionality is very generic, right? And something like which hardware to turn on, when to turn it on during the boot, that the Linux kernel will not know. It's an abstraction. Think of Linux kernel as an API that can do addition, right? So the thing that can do addition, you need to first of pass it x and y. That's one thing, but the value of x and y needs to be decided by somebody else, right? So the Linux kernel can do scheduling and management of hardware. It can help you with that, but someone needs to turn on the basic hardware that the kernel can sit on, right, or operate out of. So that's DRAM. So who will turn on the DRAM? Well, some part of ROM or later stages of the boot. So you must have noticed that when the system turns on, it kind of, well, before the screen comes up, it kind of goes ahead and checks if a RAM is available, if the timer is available, so on and so forth. And if something goes wrong, you see a message on the screen saying, hey, there is no RAM, cannot boot further, bye bye, right? So all of that kind of checks are coming from here. And the ROM code cannot be modified. That is why this has like very bare minimum stuff that is absolutely necessary for any system to boot. Now, once this happens towards the end of the ROM code, like as the ROM code's execution comes to an end, what the ROM code will do is instruct the CPU to copy some other code into the DRAM. And I should also mention that the ROM code is involved somewhere in ensuring that the DRAM is turned on. Right? So the DRAM is active by the time the ROM code is exiting, or the frequencies are set correctly, and so on and so forth. So DRAM is active, ROM code is exiting. So the ROM code will fetch some more code, put it in the DRAM, and then the CPU will execute that code. And that code, what it does is it kind of prepares more hardware. Maybe it provides user with certain security configurations during the boot up, the BIOS settings or the UEFI or U-boot environment that you guys would have seen. That is coming from this intermediate code, so to speak. So this code is essentially then offering user to select between OSs and things of that nature. All right. And now what happens is this code, as it is completing its execution, as it is coming towards like an end, it will copy over the Linux kernel somewhere in the memory, right? Uh, Kernel. And then what it'll do is it'll ask the CPU to go execute that kernel. It's like, hey, whatever the kernel requires, minimal hardware that I have enabled, you can now go ahead and execute the kernel. I've copied it in the RAM for you, right? Okay. So now we also talked about that the kernel can handle certain hardware, right? It can help us manage hardware. Now what happens is the kernel internally has lot of drivers, right? Which the machine makers like Lenovo, if it has a Lenovo camera on the laptop, so these guys will ship, or rather, take their drivers and submit it to open source as part of the Linux kernel. So whenever you're booting up the Linux kernel, the Linux kernel kind of has the driver for that particular camera already. In most cases it does. If it doesn't have, we have to add the drivers much later. That piece of hardware wouldn't be functional until that hardware is manually added much later. But right now let's talk about the drivers that are already present. So let's say something like the USB driver will already be present, right? So now the idea then is, the Linux kernel got the control, but it needs to know where the hardware is. In fact, what all hardware does your system have? Right. And let's now add in more hardware here. Let's say we have two USB ports. So someone needs to tell Linux kernel information about what all hardware is available, which is the make, what is the hardware, what driver to use for it, some hint related to that is required. And now comes the concept of something called DTB, which is called the device tree blob, right? So this is a data structure. Uh, mm, this is a data structure, and this data structure in a tree-like fashion describes who is connected to whom, what all hardware is available, at what memory address is it available, so on and so forth. So remember the intermediate code, the UEFI or the BIOS code that we were talking about. So that code also passes some other information, and there is like in SSD we'll have something else which is called the DTP, and that DTP is also passed to the Linux kernel by this software here, the intermediate code here. And this intermediate code, by the way, is called bootloader, right? So it is helping in the boot stages, prepare the machine for the OS. And so the bootloader essentially passes, so bootloader passes, the kernel, the DTB. Right. And how does it pass? So it simply says, hey, CPU, I'm going to go now. My time has come. But remember to fetch the code from this X address in the memory. That's where I have put the Linux kernel for you. And oh, by the way, also save this information about Y. And if the Linux kernel needs it, it'll come and look. And where is this Y information stored? It's stored within a few of the registers, or one of the registers, let's say R1 of the CPU. So CPU has some internal registers which it uses for bookkeeping. So one of the registers, or 64-bit worth of memory, that kind of stores the address of where the DTB is loaded. So you can now imagine that as we turn the laptop on, the boot code or the boot ROM code is executed first. Certain basic checks are done. RAM is present or not, XYZ power supply is enough or not, so on and so forth. Once those checks are done, the boot ROM copies over the bootloader, right? Copies over this bootloader and puts it in the DRAM. And DRAM is also activated by the boot ROM. So the DRAM is ready. The bootloader is loaded there. The bootloader goes about turning a lot of things, on, collecting some initialization information, and then it composes or copies over this DTB, puts it in the location in DRAM, copies over the Linux kernel, puts it in the DRAM, and before it exits, it passes CPU that information. It sets, so to speak, the program counter to the Linux kernel address, and it loads one of its internal registers with the information about where the DTB is. And once the DTB information is available and the Linux kernel starts to boot, the Linux kernel reads the DTB and figures out, okay, which USB port, who is the maker of it, what is the driver, do I have the driver? If I have it, run it, right? So that's how we have the Linux kernel booting up. And if it has the device drivers, it will use those. If not, it needs to be manually loaded. And as part of this journey, part of this series here, we are going to focus on how to write a device driver, and assume that you're writing it for a hardware that is right now not released in the market. So you're writing that device driver, submitting it to the Linux source, and while it is submitted to the Linux source, the hardware is released to the public. So as the public, gets a new laptop, downloads the Linux kernel and installs and runs it, the driver is already available and the hardware just works, right? So that is the idea. And one thing that I want you to remember about Linux kernel as a mental model is the Linux kernel is simply doing process scheduling, and it's also doing hardware management. And the drivers part typically comes when we are talking about hardware management. And before we go, remember I mentioned that the Linux kernel is like the add API, for example, which adds to number X and Y. You can imagine instead of maybe x and y, it's just, let's say, y, and it simply adds y plus 1 and returns back. So this y you can think of as the DTB. It's a parameter to the Linux kernel that it needs to be able to understand what all hardware is available, right? So with this, we kind of have the imagination and the mental models that we need in terms of reason about device drivers and start to develop the code. So with this, I'll see you in the next one.